Now let's talk about gathering data, and specifically let's focus on gathering data remotely. Let's talk about using SNMP and RMON to gather data. So let's talk about our logging tools. If you type terminal monitor, it lets you see console messages when you are connected via Telnet or Secure Shell. So, you're sitting at the console and you start seeing all sorts of messages, and you need to make a terminal, you make a TTY or VTY connection, and you're going, I don't see anything, that's why. You need to say terminal monitor. Logging console, this lets us specify the message types to show on the console. So we can say logging console whatever level. Talk about the levels in a moment. You already know the levels. Logging buffered, now, and we can also say level here, this is how much of a router's RAM will be dedicated to logging, as well as what are the message types. We can show logging to view the logging messages in a buffer, and we can clear logging if we want to clear the buffer out and start fresh. The older entries, if we fill up a buffer, obviously will be deleted to make room for new entries. Something we know very well already, the logging severity levels. So we can, depending upon the level we specify, we can have certain amounts of information. If you say level 0, the router is going to be dying before it's going to send you a message. So that's for emergencies. If you say level 1, then really important alerts are going to show. And of course, the higher up you go, it will show the lower level messages as well. What we're talking about is how verbose do you want to be. So if we only care about an emergency or an alert or something critical or something that's an error, we'll choose one of these logging levels here. If we want to also start seeing warnings and everything below, we'll choose logging level 4. If we also want to see notifications, 5. If we want to see informational, 6. And if we want to see the details of every little thing that goes on, that's when we start debugging. That's the highest level, level 7. So we could see an example here. Let's say that we set the logging level to warnings. So let's go back and look at the command here. We could say logging console 4. And then if we did a show run after viewing a bunch of the config, we could see logging buffer and logging console. We're seeing warnings. We also obviously did a logging buffered 4 as well. And so we did a logging buffered, and we have 4,096 bytes for the buffer, and we're collecting warnings on down. So if we want to capture errors, we could say logging console errors. And so we can see that if we say logging console question mark, that shows us we can choose from 0 to 7. Or we can choose alerts, critical, debugging, which we can see what the equivalent number is. So if you go, I don't remember what 4 is as opposed to 5, not a problem. You either just say logging console space question mark, and you just see right here, or you can see like the alerts, the critical, and then you can map them. Alerts are severity 1. Emergencies are severity 0. This is the system is unusable. Whereas with an alert, immediate action is needed, or critical, condition is critical, or we're getting debug messages, or errors, we have errors, or we're filtering. So we can choose different things. Notice some of these, of course, are not severity levels, but we can choose them. We can configure that with the logging command. Notice we can also log in XML as well if we wish to. So same thing with logging buffered, but what we'll do with logging buffered is we'll say logging buffered, and then we'll say the size of the buffer, and then if we want, the severity level. And the size of the buffer is in byte size here. So from 4 kilobytes on up to, well, whatever this is, 1, 2, 3. This looks like it is a kilobyte, a megabyte. This looks like it's up to 2 gigs. Pretty big log. Better have enough space. And then, of course, it shows us the alerts, the criticals, the debugs, the emergencies, etc. Now, in a production environment, you should be sending your logs to a Syslog server. And so here we would say logging, and then we would put in the IP address of the Syslog server. And we could say what messages we want to say. So like logging trap, which means we want to send debug information in this case to a Syslog server. This of course means you're generating some traffic. So when you do this, probably want to isolate that onto its own VLAN temporarily. Anyway, it will also, so we'll generate a lot of traffic, but at least it's all being captured by the Syslog server, which we can go look at later. Here is a screenshot of just the Kiwi Syslog server. It's free, and you can get it from kiwi.syslog.com, and you can set it up, and we can see that messages are coming in. So let's use SNMP now. You can monitor and configure along with RMON and Syslog. And we have different options. It depends upon the device manager menu. We can set traps, which means if there's an event here, we'll send some kind of notice to the Syslog or to the SNMP server. And we can gather information from those traps. Now remember, with SNMP, you start out with an SNMP manager and some kind of network management system here. And that NMS is going to be polling, questioning the devices round robin style. How heavily utilized is your CPU? What's the last DHCP lease you gave out? How congested is blah blah interface, et cetera, et cetera. And it'll go round robin and it'll display this on a central console. We've of course had SNMP forever. And with all Cisco devices, SNMP is on by default. So you can see that we have somebody sitting here with an NMS right here, and on a switch device, switch, router, hub, whatever, and it doesn't have to be Cisco, it can be other kinds of vendor devices, including servers. We have some version of SNMP running, version 1 or 2C, those are the clear text ones. Anything higher, we start encrypting. And so this monitor is going around and it's querying the agent, the SNMP agent that's running on the device, asking it questions. And the agent will respond, and if we require authentication, pending successful authentication, it'll respond. So we can get, or we could even set information. So with SNMP, we can get to query information, and we can sometimes set commands as well. So here are the commands to set up SNMP. We go to switch, router, whatever it is. We configure terminal, get ourselves into global. And then we say SNMP TAC server, user, and we're going to create a user account. And be whatever user, Tony, Sally, Betty, Joe, whatever. And we're saying network admin authentication, auth, SHA, and then a password, whatever the password is, ABCD1234. I hope your password's not that simple. The SHA means we'll use the HMAC secure hash algorithm 96-bit authentication for the password. Basically, we're hashing the password using that hashing algorithm. And then we can go to another device and we can set up SNMP server. We can have a user, Karen. And in this case, Karen is using MD5 to authenticate. So here are some examples for setting authentication. We can also see that we can set up the SNMP server here, and we can have a user called Moo. And Moo is using SHA with a password, and we have set some privacy levels as well, some encryption for it. Or we can delete Moo and all of Moo's associated parameters. No SNMP TAC server user Moo, and no SNMP TAC server Karen, role vSAN admin, so Karen cannot be this particular admin. So different ways of setting up SNMP. Here would be a configuration example here. Now we're primarily focused on device statistics, device health. SNMP is, we know that we have a MIB, a management information base. It's a series of questions basically that are appropriate for the device to get a snapshot of how the device is doing at that moment, which is why it's good for checking device health, and then we can gather trends over time. We've got SNMP on practically all enterprise devices, pretty much all Cisco devices it's on. So let's say we go to a router in global, SNMP server community. Now here's the thing, with community you have to say what the community string is. In the early days of SNMP, you didn't want the wrong manager querying a particular device, so a device had to belong to a specific community. And the manager and all of its little devices belong to the same community. And if they didn't belong to the same community, then the device would ignore the manager because you're not part of my community. So in this case, we're going to the router, and the router is saying, I belong to community TSHOOT. And this is read only. And my SNMP server host is 192.168.12.2 version 2C for the TSHOOT community. And then additional information, which is just nice to have, the location is Los Angeles, and the contact is some email address. This just kind of helps you when you're looking at this to see where this is. I can send traps. Now, SNMP on a router, on a Cisco router, there are all sorts of traps we can send. Traps are basically when some service or process needs to send some kind of information because it had an event. We can set traps. We could show run, pipe, include traps, and we could see all of the traps that are enabled already. So including link down, link up, cold start, virtual routing redundancy protocol. We can see for TTY and EIGRP and inserting or removing flash. And I mean, there's a lot of them, ISDN, BGP, ATM, serial ports. So I mean, there's a bunch of traps that we can include. This isn't even all of them. So now let's talk about RMON. You don't have to use SNMP if you don't want to. You can use RMON, and RMON has a threshold manager. It helps us configure the threshold for a specific event. So it activates the notifications or the log entries. So we have a device manager or a fabric manager on a switch or whatever, and it can identify the Syslog server. So it will be responsible for sending different events, like configuring call home. It can send an alert via a message or a page in a particular event. That's RMON. If we're going to configure RMON, here is some of the syntax. Get into global. We could say RMON event 2 log trap. And so what we're doing is we're creating an RMON event number 2 to define critical errors and generate a log entry, because we can see the description critical errors right here. The event trap description is critical errors when the event is triggered by the alarm, because remember that level 2 is an alarm. A user called test2 owns this whole thing. So they own the row that's created in the event table. And so this also generates the SNMP trap when the event is triggered. We can know RMON event 2, 5, or whatever to remove a particular entry from the RMON table. We can see the syntax for setting an RMON alarm right here. Go into global. We'll create an alarm called number 20. And this number right here is a MIB number. Now, of course, it means you need to know what the MIB numbers are, and that's a little bit hateful, but anyway. And we're basically saying that every 900 seconds, we actually have a typo here. And we have a rising and a falling threshold here of 15 and 1 second. So check every X number of seconds until the alarm is disabled, and check for changes in the variables rise or fall. So the software will trigger an alarm within these thresholds here. So the alarm is going to trigger an event, which we have configured with this RMON command. And we can also possibly set an SNMP trap as well. If we want to turn this off, we could say no RMON alarm. In this case, we're turning off alarm 2 as opposed to alarm 20. Another thing we can use, and this isn't necessarily remote, but it has a remote companion to it, is the spanning port analyzer, the switch port analyzer. You've probably set up span on a switch before. We know that switches, by their nature, are only supposed to forward if a particular MAC is on a particular port. So it builds a MAC table, right? Or we can call it a CAM table. It learns or builds this CAM table by listening to traffic coming in, layer 2 frames, and it basically builds a little table saying, I heard MAC this on this port and MAC that on that port. And so if somebody wants to go to this MAC, it looks in its table and it goes, oh, I'll just forward the frame out here. If you want to capture all the traffic that's going to a particular port, you'd have to put a sniffer right there, wouldn't you? But the problem with putting a sniffer there is that this is a full duplex port, I hope. And if you put a sniffer in there, you're no longer full duplex 2 point-to-point links here. You would probably insert like a hub. Now you've turned that thing into a half duplex connection. So that's not very good. So how do we plug in a sniffer on another port and listen to what's going on in this port? Well, you could poison the ARP cache or poison the MAC table of the switch, but we don't want to do that. I mean, we might want to do it if we're hacking, but not in normal operations. So we can turn on the switched port analyzer, SPAN. And with SPAN, here we are running Wireshark or whatever your sniffer is on some laptop, tablet, desktop, whatever. And there's traffic actually going between a client and a server, but we have configured the switch to SPAN to basically repeat the traffic out to us as well, so we could capture it. So how would we set up SPAN? And don't mistake this for spanning tree algorithm, it's something totally different. Go into global on the switch, and then we could say monitor session 1. We're just basically making up a monitoring session. This number, you pick whatever number you want. We can say the source interface would be gigabit 01. And then in monitor session 1, the destination interface is gig 03. So if we go back here, we can see that the source is gig 01. In other words, stuff coming from the server, the destination comes out 03. Then we go ahead and we save it. And then when we show monitor, we can see that we have gig 01 and gig 03. So now how do we do this remotely? This is really cool. We can RSPAN. With remote span, let's say that we're not right on that switch. Like we go backwards a little bit here. We could see we're tapped right into the switch where the client and the server are. But in production, that might not be the way it is at all. You might be a good switch away because the server could be over here on some other set of switches, some other switch. And maybe there's a trunk link here. So what we'll do is we will set up remote span. We have to set it up on the switch where the traffic's going through and the switch that we're forwarding to. And then we're plugged into this one running Wireshark or whatever we're running. To do that, we've got switch 1 and switch 2. Now let's go back here. So switch 1 is where the server is. That's the traffic of interest. Switch 2 is where we are. In switch 1 now, you really should separate this into its own VLAN so there's no interference. Will it take up backplane bandwidth on the switch? Yes. Will it take up trunk port bandwidth or trunk link bandwidth between the switches? Yes. But at least it's not going in and out between normal traffic. Set up a VLAN, whatever you want, something unused, like go into switch 1, which again is where the interesting traffic is. Make sure that this VLAN doesn't already exist. Go into global, create a VLAN, VLAN 20, VLAN whatever you like. Give it some kind of name, call it RSPAN, whatever you like. You don't have to give it a name, but names are good so that they're descriptive. Then tell it to remote-span. Then go ahead and set up your session, monitor session 1 or 2 or whatever. The source is gig 01, which as we recall, gig 01 is the traffic where the server's coming in. And then notice the destination is remote VLAN 20. It is not this port, it is instead remote VLAN 20. So there's the difference. And then we have to add something else, the reflector port, saying, okay, VLAN 20, but what port is it going to come out of? In this case, it will come out physically out of gig 03. So if we go back here, it's coming VLAN 20, but out gig 03, which we presume is a trunk port, which, by the way, hopefully carries VLAN 20. Don't prune VLAN 20 out. Be careful of that. So I have said where the server traffic is coming in, the traffic of interest. It's going to VLAN 20, and it's physically coming out this reflector port, which is coming down to me on my other switch. Now I go to the other switch, the one that I'm connected to. So I'm on switch 2 here. And of course, I'm creating VLAN 20. Now, if you have VTP, probably the switches have told each other already. But if not, you create VLAN 20, you give it the same name, whatever. You tell it it's remote span. And now you can create a monitor session, whatever session you like. The source is not a particular interface, it's remote VLAN 20. So you see how the switch where the server is, the destination is remote VLAN 20. The switch where you are, the source is remote VLAN 20. See how that goes? And then you can say the destination is interface FA5/2, because if we go back, I'm plugged in to FA5/2. So that's how we can do RSPAN. So here would be an example here. We have both of these happening together. We can see the whole thing that we just discussed here. Here on switch 1, I'm setting up VLAN 20 right here. Give it a name. I'm telling it it's remote span. I am creating a monitor session with an inbound interface, gig 01, an outbound VLAN 20 going across the trunk. On this switch here, I got to have VLAN 20 also. And of course, it is a remote span as well. And the source is now VLAN 20. The destination is the port I'm plugged into. You can also do this with routers. Now, you can also create generic routing encapsulation tunnels, but if you wanted to forward router IP traffic, not simply layer 2 Ethernet traffic, you could use something called router IP traffic export, RITE. With RITE, it's not a switch that's between me and the server and the user, it is a router. And so my commands will be a little bit different. So in this case, I'm going to the router, and in global I'm saying IP traffic-export, and I make up some profile name, any name you like, profile, my export, something, whatever. I'm then saying what interface, and notice int gig 0/0, and if we go back here, we can see that int gig 0/0, now here's where I've got to say where to send the stuff. So it's int gig 0/0. And then here, MAC address, whatever, whatever, whatever. Now what this is, int gig 0/0 is where you're going to send it out of, and this MAC is actually the MAC of the node that has Wireshark running. It's the node of it's the MAC of the sniffer. If you want it to be both send and receive, then we need to say bidirectional, because by default it's only the incoming stuff. And then if you want, you can create an access list. So we can say incoming access list. We can make up an access list if we want to limit what we're capturing by access list. Now we'll have to then go, once we've set this up, we'll have to go to gig 01. Let's go back. Here's gig 01. That's the one connected to the person of interest, the web server. We go to gig 01, we say IP traffic TAC export, apply this profile that we created before. So we're creating a profile, and it's saying where to send it out and the MAC of the sniffer. Do we want it bidirectional? Do we want it based on an access list? And then we apply that same profile to the port where the interesting traffic is. And then we'll see a message, activated IP traffic export on whatever the interface is, but it won't be fast Ethernet, it'll be gig. Here's another command that we have seen many, many, many times, and that's CDP, show CDP neighbors. And in fact, you will probably be expected in the exam to use CDP to be able to verify the topology. Now, we already know what the topology is supposed to be. We don't know if it has been configured that way. I can tell you this, it'll be physically configured that way. Will it be logically configured? That's a whole other story. So we will use show CDP neighbors, and we know that if we show CDP neighbors, remember CDP is a Cisco proprietary layer 2 protocol. It goes in and out of any switch port, or any, actually it's a layer 2 thing that goes out in and out any port, pretty much any Cisco device. And what we do is we use it, and it's totally independent of what the layer 2 protocol is. It doesn't matter if it's Ethernet or what. It doesn't matter if it's on, so long as the link is physically up, it carries itself. It doesn't have to be transported by anything else. So we get these CDP PDUs coming in, and we can see then, and we get it on all of our live ports. Every port that's up will receive and will send out. So we can see our neighbors here, and of course here's information about it. Here are all the little codes. So here we can see that switch 1, fast 00, that we have this device over here, and we can see what kind of device it is. It's a 2960. And then on, and it's on their fast 024. This is wrapping actually. And on our serial 000, we can see that we also have router 2 coming in as well. So we can see our CDP neighbors. Here we see show CDP neighbors detail. Of course, we do this as early as the CCNA class. It's something we learn very early on. We can see that the neighbor has a device ID of switch 1. That's its host name. It has an IP address of 192.168.1.2. Obviously, it's management VLAN interface. It is a WSC 2960 24 port. It has IGMP on. We're seeing it on our interface, FA00, and its interface is FA0/24, and we've had this for 153 seconds. We can also see that it has a particular software image and a particular version, and then we can go on from there. In an enterprise environment, it is really crucial that all of the devices have their clocks synchronized. It's not because routers need a clock to forward. They don't. But anytime you want to timestamp a message, looking at debug output or traps or alerts or whatever, you need to see the real time it happened, and you need to have all devices agree upon that real time. Otherwise, it becomes impossible to effectively look at debug output with things with different timestamps. So here's where a network time protocol, NTP Server, comes into play. We know this in other types of operating systems that it's critical to synchronize to an NTP server. We can also synchronize right here. We can go into global on our router or our switch or whatever, and we can say clock time zone. First of all, we can set the time zone. So in this case, example, it's Eastern Standard Time, 5 hours behind Greenwich Mean Time. We can also set the summertime, Eastern Daylight Time, recurring on the second Sunday of March at 2 in the morning and ending the first Sunday of November at 2 in the morning. So we know when to apply daylight savings time or not. We can then say, which is our NTP server? And we can list a couple of them, and we can even prefer one of those. And once we've set this, we can show NTP status, and assuming that we could reach this NTP server, we can see the clock is synchronized. And we can get information. We synchronized it from this thing, and we can see the clock skew, basically. So here would be an example. With NTP, the service-timestamps would add a date and time to the debug and the log output. So we could service timestamps, debug, date time to the millisecond, the local time, show the time zone year. And so with this, we can then see that in front of all of our output, we have a timestamp, May 16th, 2014, at 15:16:23 to the millisecond Eastern Standard Time. And so this is extremely useful when we're comparing debug output between devices, or even it's just like, when did this exactly happen again? This is why we want to synchronize. Now, in real life, here's what you do. You don't have all your routers go connect out to, some external atomic clock. Instead, you have one router go out to an external time source, and then everybody else slaves off of that one router. So here's an example where we have the timestamp showing when the link changed state. At this moment, we saw someone shut this interface right at this moment right here. And we saw the line protocol went down, changed state to down. The next thing we're going to talk about is something called Cisco NetFlow. Now, NetFlow, and you're going to need to know a little bit about it, this is something we find on high-end devices. It's focused on traffic statistics, network traffic statistics. And it can distinguish between what we call traffic flows. Those are series of packets from sources to destinations. This helps us ensure compliance with any service level agreements, SLAs, we might have. If the SLA says we have to allow X amount of bandwidth or quality of service, NetFlow will help us with that. We can also see trend monitoring, and we can do performance troubleshooting as well. So we could see an example here. We've got something down here running a NetFlow collector, and then maybe we've got a phone going through a Cisco switch and a router, going to a unified communication server. Now, this is voice over IP. It's got to have as little latency as possible, so NetFlow will actually allow us to watch the traffic flow between this phone and this UC server, which is basically where we're aggregating and managing and switching the phone calls, as opposed to this web server, which is going wherever it's going. So with NetFlow, we can monitor the traffic flows here, specific traffic flows. So with NetFlow, it uses a UDP destination port. There's no default. You need to specify the default, and here's how we do it. We go to the router or the whatever it is, and the switch, the multi-layer switch, and we go into global, and we say int whatever interface we want. And basically, this is for the flow coming in. So if we look over here, let's say we were doing it on this switch. It would be this interface, the flow coming in. And then we have an egress also, so we could have ingresses, and then we would have egresses. So in this case, I am watching the flow coming in this interface and this interface. And then I am exporting out from my particular loopback, and I have a particular version of NetFlow here, to a destination, which is wherever. And we're using port 5000. So in this case here, I'm saying that I'm exporting from loopback 0 using NetFlow version 5 to this particular destination, 192.168.1.50, which is where I'm collecting all of that NetFlow information, and it's sending it to me on UDP 5000. Then we can actually view this stuff. We can show IP cache flow, and we can actually see the flow of traffic. And it's organized. We see that there's some telnet traffic here. We can see in seconds the amount of flow packets. We can see HTTP traffic. We could see other UDP traffic. We could see TFTP traffic. We could see ICMP traffic, etc. So we can see all of these flows. There's also a feature on some devices called Embedded Event Manager. This lets us set up our own event definitions. So it's one thing, we're going to set up events, but what if we want something extremely specific? We can specify our own events. We can set up custom responses to those events. And the event could be a trap was raised, a Syslog message, somebody issued an iOS command, some interface counter hit some threshold, some timer went off, we have some kind of SLA or NetFlow event. Those could be any of our triggers for our event that we define. Then what's the response? We could send an email message. We could execute an iOS command. We could generate an SNMP trap. We could even reload the router if you want. We could set up Syslog messages prioritized. We could switch to a different processor in a redundant platform. We could request system information like show tech support, show process CPU history. So here would be an example of configuring it. Go into global and then say event manager, and then whatever you want to call this, applet counter reset. And so then we'll say the event, and we want this command line pattern clear counters. And so we want to make sure that if this occurs once, don't skip it. Then the action is if we have a Syslog priority, we're going to have an informational message Please update network documentation to record why the counters were reset. Then we can clear the counters, and we can do a show int to see that all the counters were clear. So like in this case, we did a clear counters right here, and the applet was counter reset. And we said clear counters is what we're calling this thing, this pattern, clear counters. So when somebody types clear counters, this pattern matches. And notice it's going to throw this message right here. Please update network documentation to record why the counters were reset. And of course, it go to the console, it can go to Syslog server.